So one way to add this digital control is with the help of a cascode element. The cascode element can help in enabling or disabling action of this main transistor. Cascode element digital control. By using cascode elements, it is very easy to convert any power amplifier with a digitally controlled on-off switch. And now by having multiples of these unit cells, we can actually have a digitally controlled envelope while the phase modulated signal is directly fed to the input transistor. The unit cells with Cascode to enable digital control. There is a downside here. The downside is this cascode element is also going to need some extra headroom, which may not be desirable in many cases. Now for power combining, depending on what is the class of the PA we are using, we need to accordingly choose the topology. For a simple case where, let's say, this MOSFET is operating in class C and this cascode element is used to just turn on or off a specific unit cell, then what we can do is we can just combine all the outputs of the various unit cells in the current domain. Then we can feed it to the load. So this current domain addition is possible for some of the power amplifier classes. So there is a lot of literature which talks about this power combiner at the output of the PA. Output of unit cells can be combined by connecting them in parallel if the PA is acting like a current source, which is possible in class C kind of operation. Okay. So a class C power amplifier with a cascode element, so can be easily connected in parallel to start acting like a digital power amplifier. Now, what happens when the input element switching doesn't look like a current source but looks like a voltage source? In such a scenario, we can see that the equivalent circuit will look like as if you have a square wave being fed to the load, and if you want this load to only see the sinusoidal output, then a simple solution can be to connect a band pass filter like this. This is the load C and L. This is the case when switching element acts like a voltage source. So here, this is the input V in our case. So this V in looks like a square wave going between 0 and VDD. When it passes through the series LCR circuit, then taking the output across the RL will result in a sinusoidal output, because this LCR circuit is going to look like a band pass filter. Like a PPF output with center frequency FRF to be equal to 1 by 2 pi root over LC. So we can start with this square wave voltage source, and output will look like sinusoid because all the harmonics are going to be filtered out by the bandpass filter. So this looks like a good candidate for switching PA, because now the input is switching between 0 and VDD. So if you use the MOSFETs as switches, then they can operate in class D or class E mode, so as to get very high efficiency, and at the same time output we are getting a sinusoid without any harmonics. Now if we start with such kind of a configuration, then we need to also worry about how we are going to handle the amplitude modulation. So one simple way to change the output power is by changing the swing of this voltage source. But changing the swing of this voltage source will require either to use voltage regulator or add some extra drop in the switching path. Both of these approaches may give rise to lower efficiency because the source itself will be dissipating that extra power. So instead of changing the switching source, what we can do is we can try to modify this network itself so that the effective voltage source, which is appearing from the load side, will have a reduced swing without actually requiring the voltage supply to be changed. So for example, this simple square wave can be generated with the help of an inverter circuit. So at the input, can have this square wave, and the output again we are going to get this square wave. The good thing is at the output now it can source and sink much higher current as compared to the input. So such a circuit can be used in place of this input source. This is your V in, and if we connect this circuit here, then the output voltage VO is going to be equal to the sinusoid component in this square wave, assuming this square wave is also having the fundamental frequency same as the center frequency of this band pass filter. Then we are going to get voltage output 2 by pi and it's going to be sinusoidal with some phase component. By controlling the phase of this square wave, we can actually control the phase of the output. So this we have already seen that in the case of switching amplifiers, we can control the phase modulation, but there is no control over the amplitude or the envelope of the output signal. The output amplitude to be related with AM. One way to do the amplitude modulation is by controlling the supply and result in extra loss. The circuit to control the supply can be a linear regulator, where the extra voltage is going to drop across another element, resulting in a reduced value of VDD, so that the overall efficiency may come down. Efficient. Another approach is to try to change the effective source strength looking from the load side, and that can be done by doing some change in this load network. Modulating load network to change the effective strength of input source. The idea is we are going to do some modulation in these lossless components, so that without adding any extra power dissipation or extra voltage drop across a lossy component, we can still control the output power. If we look at our earlier circuit, we can see that it has a source, capacitor, well, Here is the output voltage. So if you want to change the looking in impedance from the load side, what we can do is we can create an impedance division with the help of this capacitor such that looking from the source side, you will be having an equivalent source with a reduced strength, and as a result of which we will expect that the output load will also be having a reduced amplitude. So we can club this capacitor along with the input source, and then we can modify the network such that we have this capacitor in series. We'll also add a shunt capacitor. Let's call this C1, C2. This will have a Thevenin equivalent of, again, a single voltage source with single cap in series. And this voltage source value is going to be equal to V in C1 by C1 plus C2. Whereas this looking in Thevenin impedance is going to be just this C1 in parallel with C2. This is going to be C1 plus C2. Now we can see that if C1 plus C2 is maintained to be equal to C, in such a scenario, the load network is not changing, but we are able to scale the input strength by this factor C1 by C1 plus C2. So this is the idea behind new kind of digitally modulated power amplifier, where we do the cap switching to control the output envelope instead of trying to put either more unit cells in parallel or by controlling the power supply. Here input strength is determined by cap ratio C1 by C1 plus C2 C1 plus C2 can be made to be equal to C to keep the frequency response of load network fixed. So we have got this cap ratio. At the same time, we are not changing the frequency response of the load network. So the overall circuit is going to look like you have the input square wave voltage source, and then we have this capacitors, so C1, and then this is C minus C1 inductor, and the load RL, this is output. We are making both of them variable. So by making both of them variable, you're keeping the total capacitance constant while scaling the strength of the output voltage. Now the implementation is going to look like as if we have lot of such capacitors with one plate all shorted together, connected to inductor, then a load. And the other plate of the capacitor is switching between either supply or ground. While part of these capacitors are always have their one plate tied to the ground. By controlling how many of them are undergoing the switching and how many have their switches always connected to the ground, we can effectively create this kind of a modulating source which is charging this capacitor and then discharging this capacitor at a periodic rate so as to create a output voltage where the output amplitude going to be equal to let's say this is C1 and here we have C minus C1. This output amplitude is going to be C1 by total capacitance C into 2 by pi. By controlling this ratio with the envelope of the input signal, we can generate an output with a amplitude modulation. This is also called as switched cap PA. There are various implementations of the switching between the supply and ground. As seen earlier, just a simple inverter can also do the switching between the supply and ground. But the issue is during the transition period, there can be a short circuit current between the supply and ground called as crowbar current, which can add to the overall loss during switching. So there have been implementations which can improve such switching between the supply and ground. Now let us look at a detailed implementation of the switched cap PA. As we have seen earlier, we can use simple inverter kind of circuit for switching between the supply and ground. But instead of driving them with the gate of PMOS and NMOS short circuited, we can drive them separately with non-overlapping clocks. Let's say this is phi N, this is phi P. This output is connected to capacitor. So we need to feed a PM information. At the same time, we also want to give envelope or the AM information. Here we can add some digital logic to select whether the switches are going to be switching or they will just be static, such that one end of the cap is shorted to the ground while the PMOS is turned off. This can be achieved by adding an OR gate and we can have a digital input to control the switching of this PMOS and NMOS. Let's call it T0. Whereas the non-overlapping clocks can be the other input to this OR gate. So here we can generate non-overlapping clock. And feed the page information or the PM signal to this path. So this PM will generate non-overlapping clocks, which will be causing the switching of this NMOS and PMOS, whereas this digital bit D0 will decide whether the cap is going to be shorted to the ground or will undergo the switching. Here we can add an inverter so that when this digital code is high, then the output of the inverter is low. Such a scenario, the switching signal will directly pass on to the NMOS and PMOS, whereas when the digital code is 0, in such a scenario, the input to the OR gate is going to be high. So PMOS is going to be turned off, whereas NMOS is going to connect the plate of the capacitor to the ground. So by this simple selection circuitry, we are able to enable or disable switching of the capacitor. And what we can do is this entire circuitry we can put inside a unit cell, and we can have multiple of such unit cells. Such that all of their outputs can be connected together, feeding to the matching network, which right now has a single inductor connected to the load. This is one unit cell. And we can have all this digital control coming to different unit cells. These unit cells themselves can be binary weighted. The same PM signal is going to be fed to all the unit cells. And V0, D1, Din -1. This is our AMR envelope control. whereas the PM signal is directly fed to all the unit cells. So by controlling this PM signal and the envelope control, we can create a complex modulation at the output using only this digital and mixed signal circuitry. So this kind of switched cap PA is very much suitable for CMOS process, because as the CMOS technology scales, these transistors and the digital logic is also going to scale and improve in the performance. And the capacitors what we are using here is also very easily available in a CMOS process. So depending on how we design this switching circuitry, the overall efficiency of the switch cap PA gets decided. And we can also see that, similar to the earlier cases where the DAC images were directly appearing at the RF spectrum, here also, depending on what is the sampling rate of this envelope control signal, there can be DAC images. So if you want to push the DAC images far away from the center frequency, then the analog control signals can be oversampled and fed to this binary weighted unit cells. FS. So here also we can say that we can use oversampling the push DAC images away from FRF. Okay.